Okay, so we are currently studying eigenvalue and eigenvector. So last time we discussed about some properties, the definitions and some properties about the eigenvalue and eigenvectors. And yeah, again, the meaning of eigenvector is even after multiplying the matrix A with the vector x, the direction does not change, right? So the direction does not change. And so it can be represented as ax equals lambda x. So we have a matrix A here and vector x and lambda and the same vector x. So it only changed the length of the original vector, but not the direction, right? And then this equation becomes this, right? By just moving this to left, and then it means we have to have a non-trivial vector x, because by definition we only consider the non-zero vector as our eigenvector, right? And thus this homogeneous linear system should have non-zero solution or non-trivial solution, and thus this part, which is still a square matrix, that square matrix should be singular, which means it has to have some linearly dependent columns and so on, or not invertible basically. And then that becomes the same as this in terms of the determinant, right? A minus lambda I, its determinant should be 0. Okay, and now let's get into more details about the eigenvector and eigenvalues. And then I'll just move around like between different chapters, back and forth, and then I'll not follow the exact order. I'll not follow exactly the order of these chapters. So, and then please pay attention to the story or the flow that I'm describing to you. Okay, so I will cover this theorem 2 later, and also the remaining part, and then I'll directly move to the second chapter of characteristic equation, which is just this guy, determinant of a minus lambda I equals 0. Okay. So this chapter contains some properties, basic properties about the determinant, and so I will skip these parts. And the first part of this lecture is discussing some properties of the elementary matrix, the determinant of an elementary matrix. So we have 3 different elementary matrices, like scaling, interchanging between rows, and then row replacement. And then such row replacement can be represented as this matrix multiplication, right? So this will be this corresponds to the first row operation, and then the second one, and so on, right? And then after that we will obtain another form of a matrix, which will be like echelon form or reduced echelon form, right? And then the determinant of u will be the same as the determinant of this whole part. And then you guys know the determinant of a times b is the same as the product of determinant of a times b. So this part will be the determinant of a and times determinant of this guy and so on. And then among the three possible, three different kinds of row reduction, row replacement. In the case of row replacement, what was the determinant of that elementary matrix? Row replacement. We multiply some row and then subtract it from some other row and then replace that. Replace that row with the new row. What was the determinant of it? Huh? Sign changing was corresponding to another one. What was that? Yeah, if we interchange the two rows, and then that's when the determinant gets minus sign. If the determinant of original matrix was 5, and then if we switch between the two rows once, and then it will give you minus sign. But if you do once again, another row interchanging, and then it will give you another minus sign, which will become positive, right? What about the row replacement? What was the determinant of that matrix? It was the same, right? It was the same. It was the same. Okay, so if you if you forgot some details, then please review the previous lecture given by Gilbert Strang. Huh? So you're talking about some of like this matrix 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10. Like this matrix, or this kind of upper triangular matrix. Yeah, so in this special case, determinant of this matrix will be what? The product of diagonal entries, right? Product of diagonal entries. Okay, because we first pick up this row, and then we use a cofactor thing, and then we remove it, and then by using the first column, and then fortunately, conveniently, this guy will be the only element that we consider. And then among the submatrix, we select this guy, and then we remove these two columns and rows, and so on. And thus, the only surviving element will be 1, 2, 3, 4. Yeah, and this is a quite important part, and we will come back to it shortly when studying the the characteristic polynomial of eigenvalue and eigen vectors. But anyways, row replacement doesn't change your determinant. Okay, so for the proof and in order to understand why, please go back to the previous lecture, and you will see why. And then row scaling will be what? Scaling. So although by only using row interchanging and row replacement, we can always arrive at its echelon form, right? In order to make echelon form, we only need those two kinds of row operation. But in the case of row scaling, that's needed when we want to obtain reduced echelon form. Okay, and then let's think about this determinant to any